In this video we will see iterative method to solve recurrence relations. In the last video we have seen recurrence relations and how to frame recurrence relation from a recursive function. So in this video we will see how we can solve the recurrence relations using one of the simplest methods known as iterative methods. In the coming videos we will see the other methods to solve recurrence relations like recursion tree method, master's theorem and all. So in this video we will focus on iterative method to solve recurrence relations. So here goes the first example. Let the recurrence relation you got for some algorithm is t of n is equal to 2 for n is equal to 0, or it is 2 plus t of n minus 1. This is one of the recurrence relation that we got in a previous video for n greater than 0. So let this be our recurrence relation that we got while solving a recursive algorithm. So we need to find out the complexity from this recurrence relation. So as I have told you in previous videos, whenever we say complexity, we simply say complexity, that is definitely the worst case complexity of the algorithm. So the worst case complexity. So 2 plus t of n minus 1 actually gives you the, we have to consider the worst case complexity. So 2 is when n is equal to 0. That is the best case complexity. That is the minimum time taken by the algorithm to run to its completion. But here is 2 plus t of n minus 1. So that is the worst case complexity because the complexity is pretty high here, isn't it? So that is the worst case complexity, and we usually analyze the worst case complexity of an algorithm because that is a guarantee that the algorithm will not take more than this time to run to its completion. So we will take the worst case complexity. Okay. So now we will write the equation as t of n is equal to 2. We will consider the worst case complexity 2 plus t of, so this line 2 plus t of n minus 1. Okay. See, if it is t of n is written as, see, in case of iterative method, what we do is we will keep on enrolling this terms containing t till we get a pattern, till we understand a pattern and we can easily solve it. So here t of n is written in terms of t of n minus 1. So we will unroll this t of n minus 1. Okay. So in that case, t of n can be written as 2 plus, see this t of n minus 1 is actually, so if we are substituting t of n minus 1 here, this is t of n, if we are substituting t of n minus 1, you will get, this is 2, that's a constant, it doesn't have n term on it, so it will not be affected. And when it is n here, this is n minus 1 here, isn't it? So when it is n minus 1 here, that will be definitely t of n minus 2 here, without any doubt, isn't it? So we can write t of, instead of t of n minus 1, we can write 2 plus t of n minus 2, isn't it? Now t of n is equal to, we will keep on enrolling this 2 plus, now this 2 plus t of n minus 2. See, now t of n minus 2 can be written as 2 plus, 2 doesn't have the term of n with it, so it doesn't affect it. When it is n, it is n minus 1 here. So when it is n minus 2, that will be n minus 3 here, isn't it? So t of n minus 3, and it goes on like this. So it is 2 plus t of n minus 3. So t of n is equal to 2 plus 2 plus 2 plus t of n minus 3. Okay. See, if like this. You can continue doing this till you get a pattern, but we seem to get the pattern at this moment. See, when it is t of n, it is 2 plus t of n minus 1. This is 1 and one number of 2's here, isn't it? When it is t of n minus 2 here, it is 2 here and 2 number of 2's here, isn't it? When it is t of n minus 3, it is 3 here and 3 number of 2's, isn't it? That is, we got the pattern. We can write it that if it is t of n minus some number I, we will have I number of 2's here. Agreed. That is, when it is 3 number of 2's. When it is 2 number of 2's. When it is 1 number of 2, isn't it? So it is, if it is n minus I, we will have I number of 2's without any doubt. So now see, and from this recurrence relation, we have it that when n is equal to 0, t of n is equal to 2. See, so when n is equal to 0, t of n is equal to 2. So see, we have t of n minus 1 here, n minus I here. If we want this term into t of 0, see, t of n is equal to 2 when n is equal to 0. In other words, t of 0 is equal to 2, isn't it? N is equal to 0. So t of 0 equal to 2. So we want to convert this term into t of 0 because it's already given here. So t of 0. So if this term needs to be 0, you want I to be n itself. So this is n minus n 0. So in that case, if I is equal to n, we will get t of n is equal to I is equal to n. So n into 2 plus t of n minus I, that is t of 0. Now t of 0 is 2. So n into 2 plus 2. So we got a relation that doesn't contain any term of t. Now we can simply solve it. So the equation, just like we got something like a frequency count that we used to get for iterative approaches, and that is 2 plus n into 2. So we can easily write the complexity by taking the highest degree term of n, which is simply this n. So the complexity is big of n here. So this is how we find the complexity of recurrence relations using iterative method. We have a few more examples to go. So here is our next example. T of n is equal to t of n minus 1 plus 1 and t of 1 is equal to theta of 1. So this will give you some more stopping condition. So this is the worst case complexity and we will consider this. See, so t of n is equal to t of n minus 1 plus 1. So as we usually do an iterative approach, we will enroll this, the right answer, till we get a term without any t's. So t of n is equal to, see, we will enroll this t of n minus 1. See, when it was t of n, it was t of n minus 1 here. So if it is t of n minus 1, that will be definitely t of n minus 2. Yes, t of n minus 2 plus 1. Isn't it? That is t of n minus 1 is equal to, if it was t of n minus 1 here, it would have been t of n minus 2 plus this constant 1. So I have written that here. Now this 1 as it is. So unrolling it, you can write it as t of n minus 2 plus 2. Isn't it? 1 plus 1, 2. Now t of n, I'm still unrolling it because I want an expression without any terms of t in it, so that I can easily solve it. So t of n minus 2 should be unrolled. When you unroll t of n minus 2, that will be definitely t of n minus 3 plus 1. Now this 2, isn't it? This is t of n minus 1. This is t of n minus 2. Okay, it's not divided by, but this is what the term is. Okay, plus 2. So if we are writing it, that will be t of n minus 3 plus 1 plus 2, 3. So hope you got the pattern. If it is t of n minus 1, the constant term is 1. If it is t of n minus 2, the constant term is 2. If it is n minus 3, the constant term is 3, isn't it? So definitely the pattern can be written as if t of n minus 1 is equal to t of n minus I plus I. Because if it is minus 2, it is 2. If it is minus 3, it is 3. If it is minus 1, this is minus 1. So minus 1, if it is minus I, this is I, isn't it? Now we have the stopping condition, like if t of 1 is theta of 1, or 1, simply 1. So I want to convert this term into term in terms of t of 1. So to get 1 here, I am substituting if I is equal to n minus 1. So if I am substituting n minus 1 from n, I will definitely get 1, isn't it? So t of n is equal to t into n minus I, that is n minus 1, that is 1 plus I is n minus 1 without any doubts, because I has been substituted with minus 1. So t of 1 is theta of 1, so that is theta of 1 plus n minus 1. Now we have an expression without any terms of t in it, so we can easily take the highest power term of n to get the complexity. Here the highest power term of n without any coefficient is n. So the complexity is order of n. Okay. Hope you understood. We will see a few more examples. So here goes in our next example. T of n is equal to t of n minus 1 plus n raised to 4. See, the only difference for this question from the previous ones is that in previous cases it was a constant term here. So whatever, whether n is becoming n minus 1 or n minus 2, this term was unaffected, but it is the same n we are discussing here. So whatever be the changes applied to n, that should be brought to this n also. Don't worry, we will see examples. So t of n is equal to t of n minus 1 plus n raised to 4. So we will, as usual, we will keep on enrolling this. So t of n is equal to, we will enroll this t of n minus 1. See, when it is t of n, it is t of n minus 1 plus n raised to 4. So t of n minus 1 will be t of n minus 2, isn't it? When it is n here, it is n minus 1 here. So if it is n minus 1 here, that will be n minus 2 here, isn't it? Now, when it is n here, it is simply n here. So when it is n minus 1 here, this should also be n minus 1, isn't it? Because it is the same n we are seeing here, here and all. In previous cases, it was just a constant which doesn't have n, so it was unaffected. So if it is n minus 1 here, if it is n here, this is n here. If it is n minus 1, this should be definitely n minus 1, the whole raised to 4. 4 being a constant is unaffected. So t of n minus 1 is t of n minus 2 plus n minus 1, the whole raised to 4. Okay. Plus this n raised to 4, because this part was simply t of n minus 1. Okay. Now we will unroll this. This is actually t of n minus 2 plus n minus 1, the whole raised to 4 plus n raised to 4. Now we will unroll this n minus 2. So that will be t of n minus 2 will be t of n minus 3 plus n minus 2. When it is n minus 2, it will be n minus 2 the whole raised to 4. N minus 2 the whole raised to 4 plus remaining terms. N minus 1 the whole raised to 4 plus n the whole raised to 4. So if you are writing this, you will get t of n minus 3 plus n minus 2 the whole raised to 4 plus n minus 1 the whole raised to 4 plus n the whole raised to 4. Okay. So if we enroll this further, you will get t of n minus 3 will be enrolled as t of n minus 4 plus n minus 3 the whole raised to 4 plus the remaining terms n minus 2 the whole raised to 4 plus n minus 1 the whole raised to 4 plus n the whole raised to 4. Okay. See, as we go on doing this, for example, when n is equal to some, when we enroll this, when n is equal to, if we are taking t of 0 here, so this will be t of 0, that is n minus n. Okay, we are taking the nth iteration. Then if it is n, see, we will get, okay, I will write n minus n so that it will be easy for you to understand. So t of n minus n. Then if it is n here, this will be n minus 1, isn't it? N minus 1, sorry. N minus, if it is 4, it is n minus 3, 4 minus 1. So if it is n, that will be n minus 1. The whole raised to 4, isn't it? Because when it is 3, it is 3 minus 2 here. When it is 2, it is 2 minus 1 here. So when it is n, it should be n minus 1 here. Okay. The whole raised to 4 plus etc. plus n minus 3 the whole raised to 4 plus n minus 2 the whole raised to 4 plus n minus 1 the whole raised to 4 plus n raised to 4. Okay. So n is t of 0 plus n minus 1 is 1, isn't it? Because this n and n will be cancelled, and minus 1 into minus 1 plus 1. So 1 raised to 4 plus 2 raised to 4 plus etc. plus n minus 3 the whole raised to 4 plus n minus 2 the whole raised to 4 plus n minus 1 the whole raised to 4 plus n raised to 4. So t of 0, that is when n is equal to 0, definitely no work will be done and no complexity for this, because if there is no input, n is equal to 0 means input size is 0. When input size is 0, no work is to be done. So this term can be avoided. So it becomes 1 raised to 4 plus 2 raised to 4 plus 3 raised to 4 plus etc. n minus 1 raised to 4 plus n raised to 4. See, the sum of 4 powers of first and natural numbers. Now you need to get the equation for this. Again, I will give you a tip. You don't need to remember this equation. See, sum of first and natural number. Sum of first powers of first and natural numbers is n into n plus 1 by 2, and you will be remembering that, isn't it? So the complexity is, it is in the power of n square, isn't it? And sum of squares or second powers of first and natural number is n into n plus 1 into 2n plus 1 divided by 6, isn't it? N into n plus 1 into 2n plus 1 divided by 6, and n into n. So it will be in the order of n cube, because you are multiplying 3 n's here. So first powers is, sum of first powers is in the order of second power. Sum of second powers or squares is in the order of third power. So definitely sum of fourth powers will be and is in the order of fifth power. So this is order of n raised to 5. Okay, you don't need to remember this equation. Remember the equation. If you want to see the equation, you can Google it and you will get to know it. So that's the next example. Hope you understood. We will go on to the next example. So here is your next example. T of n is equal to 2t of n by 2 plus n. Okay. So here the difference between the previous examples is, in previous examples the terms within t were simply getting subtracted or added, but it is division. So division should be carried out always. Okay. In previous case it was t of n minus 1. So you will keep on dividing it. You will keep on subtracting this. But in this case it is by 2, divided by 2. So you have to keep on dividing this. That's the only difference here. Everything else is very same. So we will see. So t of n is equal to, t of n is equal to 2t of n by 2 plus n. So we have to write t of n by 2. That is, we have to expand this term or unroll this term t of n by 2. See, if it is t of n, it is 2t of n by 2 plus n. If it is t of n by 2, it is 2, it's a constant. When it is n, it is n by 2 here. So when it is n by 2 here, this would have been n by 4, isn't it? So t of n by 4 plus, see, if it is n, it is n here. So if it is n by 2, that should be n by 2 here also. So this is how you expand it. So t of n is equal to, if you unroll 2t of n by 2, that will be 2 into t of n by 2. You are unrolling t of n by 2. That will be t of 2t of n by 4 plus n by 2. Sorry, it is 2t of n by 4. We are writing just t of n by 2. So t of n by 2 will be 2t of n by 4 plus n by 2. So here this 2 is taken outside. I am only expanding t of n by 2. So t of n by 2 will be 2t of n by 4 plus n by 2. Now this remaining n is copied as such. Got this? That is 2 being a constant has been simply copied over here. Now t of n by 2 is expanded as 2t of n by 4 plus n by 2. The remaining this n is copied. So hope you understood. So this is equal to, when we are taking all the brackets out, 4t of n by 4 plus 2n by 2, which will be simply n, then this n. So which is 4t of n by 4 plus 2n. Yeah. So for the next iteration, we will be expanding t of n by 4. So I am taking 4 outside, and t of n by 4 undoubtedly is 2t of n by 8. Yeah, 4 will be divided by 2 again. So 4t of n by 8 plus, it is n by 4. So n by 4. Instead of this n, it will be n by 4. Now the remaining 2n is copied as such. So you will get, when you expand this, you will get 4 into 2, 8. So 8t n by 8 plus 4n by 4, which is simply n, plus 2n. So it is 8t n by 8 plus 3n. So hope we got the pattern somehow. T of n is equal to, I am just copying the last equation, 8t of n by 8 plus 3n. See, if we are writing in powers of 2, 8 is actually 2 raised to 3, isn't it? So this is 3 here also. So we can write it in general terms as 2 raised to I t of n by 2 raised to I plus I into n. Because when I is equal to 3, this becomes 8t n by 8 plus 3n here. Okay, when I is equal to 3, this happens. When I is equal to 2, this happens. when I is equal to 1, this happens. Yeah, when I is equal to 1, 2t of n by 2 plus n. Yeah, that's it. See, now we want to convert, we want to get rid of this terms on t, isn't it? So, if it is subtraction, we could have easily converted that to t of 0. But since it is division, the only way ahead is we can convert this into t of 1 somehow. So that is the tip. If the term is subtraction, that is t of n is equal to t of n minus 1 and all, you can somehow get it to t of 0. But when it is division, that is t of n is equal to 2t of n by 2 and all, that is the term on t is getting divided, you have to somehow make it to 1. So in this case, if you want to make this to 1, you should get that n should be equal to 2 raised to I to get t of 1. N should be equal to 2 raised to I. So to get this value 5, we can take log on both sides. So log n log n to the base 2. I am taking log to the base 2, log 2 to the base 2 raised to I. So with the property of logarithm, I am writing it as I into log 2 to the base 2, and log 2 to the base 2 is 1. So I is equal to log n to the base 2. So I am substituting that. So 2 raised to I is log n to the base 2 into t of, now this becomes n and 2 raised to I are equal, this becomes 1. So definitely n and 2 raised to I are equal, yeah, n and 2 raised to I are equal, so this becomes t of 1 plus I is log n to the base 2 into n. So it is 2 raised to log n to the base 2, so that can be written as n raised to log 2 to the base 2 into t of 1 plus n into log n. So log 2 to the base 2 is 1, n and t of 1 is 1, so n plus log n to the base, n into log n to the base 2. So the highest power term of n here is n into log n. N into log n is bigger than n. So there is a function growth curve, and it shows you that n into log log n is greater than n. I'll try to show that in the next video. So the complexity is order of n log n here. This is actually the recurrence relation for merge sort, and this is the complexity for merge sort n log n. So hope the example is clear to you. We will see the next example. Here is our next example. T of n is equal to 3t n by 4 floor plus n by 4 is being floored to the lowest decimal plus n. So you will see how we can expand this. As usual, you have to enroll this. So I am taking 3 out. Now n is 3t, t of n is 3t of n by 4 plus n. So n by 4 will be 3t of n by, when it is n, it is n by 4. So when it is n by 4, that will be n by 16. n by 16 plus, when it is n, this is n. So when it is n by 4, we are expanding this term. When it is n by 4, this will be n by 4, isn't it? Plus this n is being copied as it. So when we take the brackets out, you will get 9t of n by 16 plus 3n by 4 plus n, isn't it? Now we have to expand n by 16. When we do that, you will get 9t of n by 16, 9t of n by 16. Okay, so we are taking 9 out. Now t of n by 16 is, t of n by 16 is 3t of n by, when it is n, this is n by 4. So when it is n by 16, that will be n by 64. n by 64. When it is n, this is n. So when it is n by 16, that will be n by 16. n by 16 plus the remaining terms 3n by 4 plus n. So when you expand this, you will get 9 into 3, 27 t of n by 64 plus 9 n by 16 plus 3 n by 4 plus n, and it goes on. So hope we can derive a pattern from this. Yeah, this is actually 27 is actually the third power of 3, and yeah, 3, this is I, the third power of t, and 16x is actually the third power of 4. So 4 raised to I, that is here in this step I is equal to 3. So 3 raised to 3 27, 4 raised to 3 64. So in this case again 3 raised to 2, 4 raised to 2, isn't it? So that is the pattern. Now n plus 3n by 4 plus 9n by 16, and goes on like that. That is, if we are taking n out, that is n into 1 plus 3 by 4 plus 3 by 4 the whole square, and it goes on like that, isn't it? So see, eventually to converge to to get rid of this terms of t, you have to get n is equal to 4 raised to I. So definitely I is equal to log n, as you have log n to the base 4, as you have seen. So 3 raised to log n to the base, I is log n to the base 4, then t of 1. When n is equal to 4i, this is t of 1 plus n into, now this is a GP, 1 plus 3 by 4 plus 3 by 4 the whole square. This is a GP with common ratio 3 by 4. See, when the GP's common ratio is less than 1, you can simply take the sum of infinite terms in a GP while finding complexity. That is, if the common ratio is greater than 1, you have to definitely found how many terms are present there and find the sum accordingly. But if the common ratio is less than 1, you can simply take the sum of infinite series. So sum of infinite series goes by the equation a divided by 1 minus r. Here a is the first term and r is the common ratio 3 by 4. So 3 raised to log 4 to the base n to the base 4. So you can rearrange it as n raised to log 4 to the base 3. 3 to the base 4. Then t of 1 is 1 plus n into 1 by 1 minus 3 by 4. So that will be n divided by 4 minus 3, 1 divided by 4. So n divided by 4 minus 3, 1 by 4. So that is actually 4n. Okay. So this is actually n raised to log 3 to the base 4 is usually the value n raised to, this is the value 0.7. So this will be n raised to 0.75, something like that. I don't remember this pretty well. Now 4n. So the highest power term of n is this n, because this is less than 1. This is n raised to 1, isn't it? So the complexity is order of n. Example is t of n is equal to t of n minus 1 plus n. Okay. So this is actually the worst case complexity for quicksort, and we will see in a recurrence relation for worst case complexity for quicksort, and we will see how we can solve this. So t of n is equal to t of n minus 1 plus n. So as usual we are enrolling t of n minus 1. So t of n minus 1 will be t of n minus 2 plus n minus 1, isn't it? Hope you don't have any confusion in it, because t of n minus 1 will be, if it is t of n, it is t of n minus 1 here. If it is t of n, it is t of n minus 1. So if it is t of n minus 1, that is t of n minus 2 here. When it is n, it is n here. So when it is n here, it is n minus 1 here, definitely, isn't it? So that's it. T of n minus 2 plus n minus 1 plus this remaining n. So you will get T of n minus 2 plus n minus 1 plus n. Okay. Now we have to keep on enrolling this till we get rid of this terms on t. So T of n minus 2 is T of n minus 3 plus n minus 2. Now the remaining terms n minus 1 plus n. So this is actually T of n minus 3 plus n minus 2 plus n minus 1 plus n. Hope you got this pattern. That is, if you are writing these terms in rows, no need. So this is subtraction. So as I told you, you can easily convert this into T of 0, that is input is 0, no work. So complexity can be easily got as 0. So to get this T of 0, what we have to do is, you have to, that is after some iteration, you have T of n is equal to T of n minus n. T of n minus n. Okay. See, when it is 3, it is n minus 2 here, isn't it? When it is minus 3 here, it is minus 2 here. So if it is minus n, it will be minus n minus 1 here, isn't it? Without any doubt. Plus n minus 2, etc. plus n minus 2 plus n minus 1 plus n. So T of n minus 1 is n minus n is T of 0 without any doubt. N minus 1 is 1. N minus n minus 2 is 2 plus etc. plus n minus 2 plus n minus 1 plus n. See, T of 0 is the time taken when input size is 0. You know that when input size is 0, no work is to be done, so it is 0. Now the remaining terms are 1 plus 2 plus 3 plus etc. plus n minus 2 plus n minus 1 plus n. That is the sum of first n natural numbers, and you know that it is n into n plus 1 divided by 2, which is in the order of n square. So the worst case complexity of quicksort is order of n square, and thus is the recurrence relation for the worst case complexity of quicksort. So that's it. Hope you understood. If you have more questions, you can ask that in the comment section. So hope you understood this. Thank you so much.